Hello and welcome to our review on electricity. So this is straight out of the grade 11 course. You'll notice that the note or the PDF that you printed off has all the note written in for you. Nothing really should be new here, so I'm just going to go through quickly, refresh memory, and that's our goal, that you can explain the concepts of electricity based on the 3U course. So here we go. So first of all, what is electricity? And this comes from previous students giving me answers or ideas. We talk about the flow of electrons in a DC setup. We talk about transfer of energy through electrons in an AC. And then we did the pretzel lab in the grade 11 course. And some people give the analogy of the water tower. Now, I haven't used the water tower analogy in a while. And it's really just for the people that had a hard time even with the pretzel analogy. But that's basically what students have said in the past. So, talking about the concepts involved here. So law of electric charges, there's 3 of them. We talked about this, that, and you've seen this probably in the grade 9 or 10 course. Opposite charges attract, like charges repel, and charged objects attract some neutral objects. So electric charge transfer. So the transfer of charge from one object to another happens because of that large difference or unbalanced amount of electrons. So we can charge in 3 different ways, and we talked about this in the grade 11 course, and I'm pretty sure you do it in grade 10 with electricity. We have contact. So that's when we have a charged object and we bring it close, and then when those objects touch, we get the shared electrons. So we came up with the 3 pictures. I'm not going to go into a ton of detail here, but basically too many electrons, couple electrons. If we then touch the 2, make contact, then we get a couple of those electrons jumping over to kind of balance it out. All right, so they're getting that balance. So that's what contact refers to. Then we have the stripping away of electrons. So that's when 2 objects are rubbed together. So that is similar to rubbing a balloon against your hair. Okay, you did in grade 10 the ebonite rod with the fur, the ebonite rod with the plastic rod with fur, so on and so forth. And the third one was induction, and that's when you're forcing electrons out and leaving a charged object, a positively charged object. So again, straight out of the grade 11 notes, they're in more detail. If you want to take a look, a refresher, you can go back to the video from grade 11 and take a look at those 3. Not really the main focus for us this year. We talked about what a conductor and an insulator is, and it's about that readiness, how well it will allow electrons to flow. So conductors, they readily allow electrons to flow, whereas insulators provide a certain amount of resistance that don't allow for those electrons to flow freely. So there is our 2 definitions for conductor and insulator. Haven't changed from last year's grade 11 course. Talking about current now, talking about the flow of electrons. And that's what the definition is, the rate of flow of electrons. When we did the pretzel lab, it was the rate in which students were going around the circuit. So we use I for the symbol for current. Its units are amperes. That's capital A. And how do we calculate current? Well, one of our formulas is I equals capital Q over S. Q is the amount of charge, and S is the amount of time. So we end up with, an ampere then, off the side, is equal to a coulomb per second. All right, so that's what our amperage is, coulombs per second. All right, that is your current, again, straight out of the grade 11 course. DC versus AC current. Don't really need the words current, it's overkill. DC is direct current, and that's electron flow, and that happens with batteries. All right, batteries are an example, probably the primary example of direct current, where AC is alternating current, and that's when the electrons vibrate, and that is your wall socket. All right. Now, when we talk about batteries, for example, laptops, you'll note when you have to plug your laptop in or when you have to plug in your iPod or your iPhone or your smartphone, that the adapter that goes into the wall is a fairly large adapter. So it's not quite the size of your hand, but it's oversized. What this does, or with laptops, they actually have a box within the connection. So if here's my plug, for example, plug, the wire goes through a box, and then the power plug into your laptop. Both of these are converters. Converters. What they do is they convert AC to DC current. So if you want to charge your battery is DC. You can't just simply plug it into the wall and let alternating current charge it. You have to have a converter. So those boxes convert alternating current into direct current, which allows the battery to charge. All right, and this has that funny view angle that goes into your phone or iPad or whatever. All right. Voltage. We then talked about voltage. Definition of voltage is the potential difference between 2 points. So how many pretzels do you have? How many pretzels do you have left after you went over the chair? So that goes back to our analogy in grade 11. How many volts did the electrons have before the resistor? How many volts does it have after the resistor? So it's how much work, okay, is necessary. Now remember, work, another word for work, is equal to energy. All right, so how much energy is necessary to move 1 coulomb of charge from point A to point B? So voltage, we use capital V for a symbol. It's joules per coulomb, and its units are in volts. All right, same as it was in the last course. Talking about resistance. Resistance. Definition is the measure of a material's opposition to the flow of electrons. So how much does it oppose the flow of electrons? We use capital R for resistance, and we use the omega symbol to represent ohms. And then at the end of the whole ordeal here, we ended up with the relationship V equals IR from the grade 11 course. You confirm that with the electrical lab that we ran, so you got to see the relationship and how actually do the calculations and confirm that it actually does work. And we talked about V equals IR. We then talked about how it's a linear relationship. So if we were to plot volts on the y-axis, we were to plot current on the x-axis, resistance is simply the slope. It's a linear relationship. We're just finding the slope of that line. So if you were to plot with a resistor, you change the voltage, you would find that the current changes as well, and that's how our R is calculated. The resistance would be a constant, and it would be V divided by I, or delta V over I. And that all comes from the V equals IR. So it is the slope of the line. So they're all tied together, and it goes back to V equals IR as a linear relationship. All right. Then we talked about Kirchhoff and Kirchhoff's laws. So there was 2 of them. The first law was his current law, and we said that at any point in time, the current remains constant. So that says that, I'll do this in stages, I1 here, all the current is going through I1. If it then gets branched into 3 different sections, then the sum of I1, I2, I3, I4 is still going to equal the total current. So it's just peeling off the current, moving it into different locations. Similarly, at this stage, there are 2 paths the electrons are on. If we were to add I2 and I5 together, it's still going to equal I1. And then when they combine, we still have our total current. So it doesn't matter where you are, the total amount of current remains constant, but it might get spliced off into different pathways. Finally, Kirchhoff's voltage law. His voltage law states that whatever you start with, however many volts the battery provides you, or if you think back to the pretzel bag, however many pretzels I give you, when you do a complete circuit, you need to use all your pretzels up. So what that means is that if we add up how many pretzels you ate at chair 1, plus the chair 2, plus chair 3, it's going to equal how many pretzels you started the loop with, or how many volts. So a 9-volt battery, that means that through here, and here, and here, V1, V2, and V3 have to add up to 9 volts. All right. So then we moved on to Ohm's law, or we talked about Ohm's law in the course. There are 2 different Ohm's laws, so to speak. There's the one for series, and if something's in series, you just add your resistors up, R1 plus R2 plus R3. If they're in parallel, you have to add the reciprocals up. 1 over R1 plus 1 over R2, and that gives you 1 over RT. All right, so it means you'd have to flip your final answer. And we have series versus parallel. So here are the two different pathways. Series means that everyone goes on the same path. I can't stray from the path, so each and every electron follows the same pathway. Parallel, I could be an electron that follows this pathway, and my buddy, my partner electron, could have done this pathway. So parallel means that there is more than one pathway that exists within the circuit. Okay? For this one here, you would just add up your total resistance, R1 plus R2 plus R3. And that would give me my total resistance. Here, R1, oops, this will be R2, R3, and R4 this time. If I want to know my total resistance here, I'm going to have to add RT equals R1 plus R4, because everyone has to go through R1, everyone has to go through R4, plus I need to take 1 over R2 plus 1 over R3. Now, normally we would have done that in stages, so you would have done this stage first. You would have collapsed this resistor here. So these two pathways, you would have combined into one big one last year. So you would have done this step first, and then you would have added it to the other one. So I'm just showing you the overall general formula to figure out the total resistance there. All right, so you're still gonna, if necessary, you can still break it into parts. Moving along, what is the total resistance in each circuit? So here are some examples. So let's take a look at the first one in series. So as I said, you're just adding the three resistances up. So 10 plus 20 plus 30. And again, the reason for that is that every electron has to follow, well, that's kind of neat, not what I wanted. Every electron has to follow the same pathway. They can't stray from that pathway. All right, and then when we look at resistance, I can have an electron that follows the green pathway. I can have an electron that follows the blue one. And I have one that can follow the red one. So there's three different pathways there. So if there's multiple pathways, that means you have something in parallel. So now you're looking at adding the reciprocal of those. So a 10th plus a 20th plus a 30th. Once you do the math, the calculator will handle that if you're having trouble with fractions. 11/60ths. Remember, you need to flip your answer because it is 1 over RT. So that means we want RT over 1, essentially. So to do that, we take the reciprocal, we flip the fraction over. All right, and that was all taken care of in the grade 11 course. A couple of quick examples here, fully worked out. Nothing changes from last year. I'm just getting you warmed up. You're going to do a couple problems to get into the swing of things here. Milliamps, remember we have to work in amps. So what I did was I converted milliamps to amps. Milli means 1,000 parts to it, so I divided by 1,000. Resistance is in ohms, so I don't have to worry about that. Plugging into V equals IR. Here's my current. Here's my resistance. We get 0.03 volts. So 0.03 volts. So that means you'd have to eat 0.03 of a pretzel to get through this resistor for this scenario. Okay, so just decoding and plugging in.